Oh, good morning. We had some trouble with this equipment. Possibly it'll drop out. If it does, then I'll switch to another room. You can get back on at the same WebEx address and I'll come back on in the other room as soon as I find out it's off. So hopefully it'll work, but if it doesn't, we'll move, just try and get right back on. I don't have the test ready yet. I'm sorry. I had time, but I had other tests in front of yours that I haven't finished yet, so I'm still trying to get through those. The good news is the material gets a little easier. There's not any more proofs. This first part today will be probably the hardest stuff that's left, so it won't be much easier. But after that, I don't say it'll be easy. It'll be more like the rest of the material from the beginning of the course. And actually, we're talking about the last topic for trigonometry today. Today and Thursday. After this week, it'll all just be applications. Things that are useful later that use trigonometry. But if you don't see them now, you can pick them up because you have the trigonometry behind them. So the last topic really for the semester is oblique triangles. What's an oblique triangle? Anybody know? These are simply triangles that are not right triangles. There's no right angle in them. So I'll say non-right triangles. We know how to solve right triangles already. And in fact, to this point, we can do what a lot of people in engineers and so forth do because they don't always remember these rules for oblique triangles. But currently, we can already solve these. But with a lot of difficulty. I want to point this out in case you forget this method or because you'll see other people do it. It's not hard. Suppose I have this triangle, which clearly doesn't look like a right triangle, right? There's not an angle that looks like a right angle. And maybe I'm given the length of this side and this angle here. And let's say this side. I can actually solve that triangle. All right. This is what an engineer or somebody might do who doesn't know these techniques we're about to do. They could drop a perpendicular through here, and if it's not a right triangle, they can make two right triangles out of it. Now, this one can be solved because you know an angle and a side out of this triangle, plus it's a right triangle, allows you to solve this one for all its parts. And now you're in a little bit of a pickle here because how do you find this side and this angle and this angle? It's a little awkward, right? You think to yourself, well, let's see. I know the sum of these three angles is 180 degrees. Well, that's not enough. I only have one of them. I know the sum of these two angles is 90 degrees. Well, and I know these two angles add up to this angle. And if you put those three things together, you can actually figure out what these three angles are, and then you can solve the rest of it. But that's a mess, right? Who wants to do that kind of thing, solving a triangle? So instead, these are very elegant, quick ways to solve non-right triangles that are used quite a lot in things like triangulation. You know, you got somebody else lost at sea here in a desert island or something, help in, but you don't know which place they're at. If you've got two locations that know their distance apart, for instance, and know and can receive the signal, they can get the angle from this location, the angle from this location, and knowing their distance between them, they solve this non-right triangle and find where that person is. Around your garden, you know, you want to know how much fertilizer you need, but you didn't make it at right angles, you made it like that. Can you measure these sides and figure out how much area it has and so forth by figuring out what the size and, you know, trying to solve a triangle can be difficult. I guess really what I'm thinking is if you have a lake here and you can measure these kind of things over here, but you can't measure the distance across, you can still find the distance across by using a non-right triangle. And those kind of non-right triangles come up in all sorts of applications. So we want to be able to do them quickly, not like this is the point. And there's two methods for solving these. That's what I'll do is I'll give you an outline here that I don't see any books do at the beginning. They always do it afterwards. All right. But so it's there, but I want to give you sort of the the picture of the model before we build it, so you know where we're going, right? One of them is the law of sine. This is used to solve lots of these non-right triangles. Right triangles are no problem. You got two sides, you got an angle on the side, you can just solve the whole right triangle. Two angles, there's not a, there's not a unique triangle defined. So, but you can solve right triangles whenever you're given enough information, but not so with non-right triangles. The law of sines will allow us to quickly solve a right triangle, a non-right triangle.
Professor?
Case that we're given an angle, followed by a side.
Professor?
Yeah.
Can you move the camera a little bit?
Sorry, yeah, I forgot again.
Thank you.
Yeah, you're welcome. Good thing I got you guys on there. All right. One of them is the law of sines. This works for when you're given an angle followed by a side followed by an angle. You can rotate around the triangle counterclockwise or clockwise. It doesn't matter. As long as it goes angle to side to angle in that order. Or if you have side, side, angle, side followed by side followed by angle. Or if you have angle, angle, side. Those three cases, the law of sines will solve the triangle quickly. Right? You don't have to drop perpendiculars and deal with multiple equations and multiple unknowns. The second one is the law of cosines. This is for the remaining cases. Side, angle, side, and side, side, side. Well, there's one more case left if you're a student, right? There's 6 different cases of 3 pieces of information you can be given in a triangle. The other case is not a congruence theorem, right? There's no triangle determined by it. So angle, angle, angle does not determine a triangle. You can scale it up 2 times as big, 10 times as big, any number of times, and no particular triangle is determined. So doesn't determine a triangle, just its shape. By the way, I should mention, if anybody hasn't got their COVID shots and wants to get it, they're giving them right across the street here, practically from the math building over in that, well, it used to be the church there that UC was bought out. St. Mary's Episcopal, I think it was. Anyway, they were having trouble filling the appointments today. So if you want to check with them, they've been sending emails around. You can get in there pretty quickly though if you want to get your COVID shot, be safe for summer. A lot of you guys aren't in a whole lot of danger from it, but it's easy to bring it home to grandma, grandpa, or something. So it's worth getting a shot, I think. All right, so I'll just mention that in passing. Here's the law of sines and law of cosines. Between them cover all the cases except for the one that doesn't determine a triangle anyway. That's where we're going. We're going to do these 2 laws and between them solve these oblique triangles quickly. Stop me as you have questions. So today we're going to do most of the law of sines. I don't even think we're going to finish it. Tomorrow we'll finish the law of sines. Thursday we'll finish the law of sines and do the law of cosines. So that's the topic for today, is use the law of sines to solve an oblique triangle. But the right triangle works too. I shouldn't say these don't work. The thing is that the right triangle methods we already learned are faster. So who would want to use a slower method to do the same thing, right? Law of sines to solve a triangle given angle, side, angle, side, side, angle, or angle, angle, side. There. To tell you the truth, even when I started teaching this, I had trouble remembering it this way. This is where all books do it, because the people who write the books know it's backward and forward. But now I know this stuff. I had to teach it a couple times before I figured it out. What was easier for me than to remember these 3 cases was, maybe I should turn this back. You can memorize this however you like. These laws both apply to all triangles, actually, but this one works quickly for these cases. And if you take it from one of these cases, it's no better than dropping a perpendicular. This works quick. The law of cosines work quickly for these 2 cases. If you use it on one of these cases, it works, but it's no quicker than using the drop the perpendicular thing. It's a mess. So use this one for the law of sines for these cases, law of cosines for this cases. How do you remember? I thought it was easier just to say, use the law of cosines if you give them side, 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 or side, angle, side. I can remember that because it has lots of sides, right? It's just this angle in the middle. And then everything else is the law of sines, right? So I like it that way. Memorize it however you want. I think this is easier. Side, 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 or side, angle, side is law of cosines. Done, right? The other thing you can do is what I used to memorize before that is, if you can somehow figure a side and an opposite angle and have one more piece of information, then you can use the law of sines. And otherwise use the law of cosines. I don't know that's quite as easy, but it was sort of natural to do it that way, as I'll show when I do the problems. All right. So let's do the law of sines. This is actually very easy. The proof is not trivial and it doesn't teach you a lot. So this one, I'm going to omit the proof. There are some proofs I'm going to do when they're insightful. Some of them, like there's one for areas of triangles coming up. And once you see that, if you forget the formula, you can figure it out because the proof is kind of easier than the formula. So some of these I'll do the proofs when they're insightful and they help you remember the formula, but this one's long. I'll just say, here's the theorem. Called the law of sines. Usually stated this way in books. In any triangle whatsoever, including right triangles, but you don't want to use it there, it's longer. And you label the triangle this way. A goes opposite angle alpha, B goes opposite angle beta, and C goes opposite angle gamma. Labeled that way, the sign of alpha, first letter of the Greek alphabet, is to A, and the sign of beta, second letter is to B, the second letter of the English alphabet, and sign of gamma, not the third letter, but it's what we use anyway, is to C. There's the law of sines. It's no harder than that. So I'll put a big star here. You memorize this to solve oblique triangles in these three cases. This is really three laws in one, right? Because one law is this. This equals this. Another law is this equals this. And a third law is this one equals this one. So it's three laws in one. And what you do now is what makes this easier than those proofs where you didn't know, oh, so try this theorem or that one. It's kind of hard to tell which way to go. This is like a cookbook. You just follow it through. If it's one of these cases, you do the following strategy to solve triangles. I'm going to move this to the other side. So the strategy is given one of those three cases, angle, side angle, oops, side angle, or angle side. What you do is one, apply the law of sines. Let's give an equation number one. I'll put a number one by the equation in this box. Apply one, the law of sines, with three of the things known in it and one unknown, to find another measurement. Now you're given three, now you know four. And you do this twice. And then anywhere along the way, you find you have two angles, like in this case, you're given two angles, and in this case, you're given two angles. As soon as two angles appear, which in these cases is right away, use the sum of angles theorem. Three angles in a triangle add up to 180 degrees. To find the last angle. And between two applications of the law of sines and this sum of angles theorem, you can solve the triangle. And every triangle has 6 measurements, right? 3 angles and 3 sides. You're given 3, you find 3. Just keep that in mind when you do all these problems. So use this one to find the last angle. It is free. You can just use the law of sines 3 times, but who wants to use this complicated law? All you have to do is the subtraction to find the last angle. So always find this one. You're less likely to apply this angles theorem. You're less likely to make a mistake this way, right? Find the last angle. That's it. You need the law of sines twice and the sum of angles theorem once as soon as you have 2 angles. Easy. But I've left out the details, right? I said the devil's in the details, right? Hey, it is actually, I told you this is actually the hardest probably day of what's left. I don't think it's as hard as the proofs we did, but law of sines has something lurking inside. Let's try an easy case first. I want to do number 1A. When you go to do your homework, you can try this one first and see what we did in class. Hopefully I won't make a mistake. Suppose you're given, and I should point out, you have to make the measurements the way they said. It does not matter which side you call A, B, and C. And by convention, in a right triangle, you're supposed to call the hypotenuse C. They use that in a lot of formulas, that assumption. So people tend to do that. But on these oblique triangles, it doesn't matter. You make C the shorter side, the longer side. A lot of times when you're first solving, you don't know which is when it's going to be the longest. So you don't want to make a requirement. You pick the longest when you don't know which one it is. So we'll just call A, B, and C randomly. And then the rule is that alpha has to go opposite A, beta has to go opposite B, and gamma has to go opposite C. In some textbooks, they prefer, instead of Greek letters for angles, they like to put A opposite side A, capital B opposite side B, and capital C opposite side C. So bear in mind, some books will use capital letters for the angles, and also for the points they're at. Then they don't have to put Greek letters in. That fashion, I think, is going away. Many years ago, when you published books, you didn't always have Greek letters available in print, so it's easier to put these capital letters. But now it seems like most books use Greek letters. So I'll erase these and say in this book, and for us, we'll just use these Greek letters. All right, here's the example. Suppose I'm given that alpha is 35 degrees, and pretty much all these will be measured in degrees. So put your calculator in degrees mode for these, so you don't make a mistake. And I should say there's a good reason for that. You know, when you're doing these things, you're a surveyor or something, and you're standing over this tree. My wife's father was a surveyor, and he was out in the Florida swamps, and he'd have to measure a distance here with his little device out this way, and then he'd measure his device out this way, and he could measure the angle between them, and then he can figure out how far it is between them and all these other things in the triangle and do surveying. But, you know, when you're out in the swamps, this angle is almost never a special angle, right? So you're always measuring things and things you can think cognitively. You don't want to say pi over 6 or pi over 17, you know. Oh, gosh, what is pi over 17? I don't know. But if instead you say 12 degrees, that I can kind of figure. So we'll measure these in degrees like we're out in the field somewhere where these things, you know, you're a farmer also. This is your plot. And you want to figure things out, but there's a lake in the middle and you don't know how far it is across, right? So those kind of things come up very commonly. It's almost never special triangles. If you're a contractor building buildings, maybe they come out special angles all the time. Or if you're a jeweler cutting diamonds, maybe they're special angles. These kind of applications are usually in degrees because measurements are usually made in degrees. That long-winded approach, let me cut off the problem. Alpha equals 35 degrees, gamma equals 73 degrees, and C equals 20. We don't know if it's the longest side, it might not be. All right. What's the rule? You start off with, as soon as you know 2 angles, use the sum of angles theorem. So immediately, just to save risk of error, I'll say beta, not that you can't make an error this way, is 180 minus 35 minus 73. Let's see, there's 108 there, that would be 72 degrees for beta. Low chance of mistake, right? So as soon as you have 2 angles, find the third angle. Now, the rest of the time, we're going to have to use the law of sines, though, right? So let's see. The object, again, in the law of sines is to use one of those 3 laws and fill up 3 of the 4 slots, so there's just one thing to solve for. I have here gamma and an angle, and C its opposite side. So I'm going to use that form of the law. I'm going to say sine of gamma, 73 degrees, is to C, 20, as sine of alpha, 35 degrees, is to A. This is
So,
called
wait.
equation.
Where did you get the where did you get the 73 degree?
The which degree?
Was that
Oh, from
included
here.
in?
I was given 73 degrees is what I'm saying.
Thank you.
Yeah, it probably looked like I was copying it, didn't it? Yeah, so, here's the trick in the law of sines: get an angle on an opposite side and put them into one of these expressions. Then another number you know here. Now there's only one to solve for. So I can solve this immediately for A. And here's a comment on other books. This is kind of inconvenient because I have to do this algebra in the following way. I have to solve for A. One way to solve for A is to say, well, if these two quotients are equal, then their reciprocals are equal, right? 20 is to sine 73 degrees, as A is to sine 35 degrees. I like to do it this way. This gets the A on top. Now I just have to multiply both sides by sine 35 degrees, multiply by sine 35 degrees on the left. Of this. And then the sine 35 degrees on the right times this leaves me with just A, right? They cancel. There it is. A is this number. I just have to run it in my calculator. So this section is going to be a calculator section. You need it again and again and again. Put it in degrees mode because almost all the problems are in degrees. Make this calculation. A equals, and here's one of the few things you have to be careful for, is to make sure you close your parentheses on these things. The new calculators usually insert 2 parentheses when you push sine, and there's not a problem. But if you have an old clunker like I do here, it'll put in 1 parenthesis and you have to close it. If you don't close parentheses on this old TI-84, you push sine 35 degrees times then all this stuff, it will automatically close the last parenthesis, all parentheses that are open, in fact, at the end, and it won't throw an error. It will just close your parentheses for you. If I can, it inserts this one automatically. If I don't insert the others, it will put one here. It'll take the sign of this whole thing. That's wrong, right? So close your parentheses by hand. Put in that closed parenthesis. And then same thing here is a good idea to close this one. If you put in too many here, if you put in this one and it gives you an error, then that means you put in too many. And that'll warn you made a mistake over here. But close your parentheses on this one or you'll get the wrong answer. That's one thing to watch out for. Okay, so I'm going to try that. First, make sure that the thing is in degrees mode. Let's see. It's not in degrees mode. Okay, now it is. So I'll take, and here's the good part. You might say, well, wait a minute, maybe I need to do the multiplication and then the division, or maybe I need to do the division and then the multiplication. It turns out it doesn't matter, right? As long as you close your parentheses here, you multiply first and this, then divide, or divide first and then multiply. It doesn't matter. So that's the easy part. Try to sine 35 close times 20 divided by sine 73 close, enter. And I get 11.995, blah, blah, blah. And now the instructions say round to 1 decimal place. All these problems are going to be rounded because we're not using exact special angles. We're just going to have to round it off somewhere, pretty much always. So how do I round to 1 decimal place? Here's the first decimal place. The next digit is 5 or greater. So I round up to 0 here, and I call this 12.0. Put the 0 on there or it's wrong. I mean, this shows that this is a significant digit. If you write 12 and give me a rounded number, I assume it was rounded to the nearest 1, not to the nearest 10th. So that 0 tells me you rounded it there. Well, that's only the first part, or the second part. I've done one, I found an angle. 2 I found a side. But there's 3 things to find, right? I'm given 3 and I find 3. That's the way this game works. So I have one more thing to find. I look for what's missing. Oh, B isn't found yet. So I gotta find D. So now I've got everything but B. I just write any relation in the law of sines that relates B. So I'm gonna need sine of beta is to B in here. I'm not gonna find B. Beta was 72 degrees. So sine 72 is to beta as, well, what should I use? It doesn't matter. I'll count anything you do right. I like to use the original numbers that I was given because the numbers I came up with afterwards rounded those numbers, and there's just a little more error. You assume that the first numbers were rounded, somebody measured them, but now I rounded again. There's this tiniest bit less error, so I'll use the original numbers when I can. Sine 35 degrees alpha is to A, its opposite side. What was it? Oh, no, I'm sorry, no, gamma and C were given. Sine 73 degrees. Remember the wrong one. Is to C was 20. So I'll use the original numbers, but I don't care if you don't. I'll count your numbers correct. But you can see now that what's going to happen on the test is somebody else is going to put sine gamma is to C over here equals this. Somebody else is going to put sine alpha is to A equals this, and they're both going to be right. But because they start with different equations with slightly different rounded numbers, they're going to come up sometimes with slightly different results. When you do your homework, if you come up wrong by 1 or maybe even 2 in the last digit, you're probably right. You probably just rounded in a different order or used a different equation. So don't worry about it. That's going to happen. So that's what happens here. If I would use sine alpha over A, I'd probably come up 1 off in the last digit or something. Maybe I'll get the same answer too. Sometimes I do. I've got the same problem here. B's on the bottom. So I'll write this by saying if these are equal, their reciprocals are equal. 20 is to sine 73 degrees as B is to sine 72 degrees. Boy, it looks like B is going to be pretty close to 20 of it, right? Because it's almost the same denominator here. So now I multiply through on both sides by sine 72, and I have sine 72 times 20 over sine 73 equals B, and I can run that on the calculator. Let's see, sine 72 closed times 20 over sine 73 closed. Enter, and I get 19.89. Sure enough, it's close to 20. These are the kind of checks that you want to do as you go along. You say, these must be pretty close to equal since they're over almost equal denominators. I better get an answer close to 20 or I know I made a mistake. Those kind of little checks as you go along really help you here because there's a lot of computations. This one says 19.89, blah, blah, blah. This digit is 5 or greater, so I round up. I'll say this is approximated to 1 decimal place by 19.9. Now I'm done. I was given 3, I found 3 measurements. Any questions on that one? Not too bad, huh? Better than doing a proof? All right. But it's more step by step is the thing, right? You just apply the law of sine twice, apply the sum of angles theorem once somewhere wherever you get, oh, this messed up. Wherever you get 2 angles now, as soon as you get them, and you're home always. Except, I told you there's a devious plot coming up here. There is some tricks to this. One trick, the smaller of the two, is like this. Suppose I am given actually, let me outline it first. The case side angle has this unfortunate thing that it brings ambiguity. There are 3 different cases that can happen if you're given side angle data. If you think back to geometry, you might remember something about those other cases I put up. If I put angle side angle, that's a congruence theorem. If I have one triangle and I know an angle followed by a sine, angle alpha followed by a side, followed by an angle, that is congruent to any other triangle that has those same measurements, alpha, C, beta. these two triangles will have all 6 measurements the same. Angle, side angle, we say then is a congruence theorem. So is side, angle, side. So is angle, angle, side, and so is side, side, side. Those are all congruence theorems. Once you know those, the whole triangle is determined. Unfortunately, side, side angle is not a congruence theorem. There can be no answer to it. There can be one answer to it, or there can be 2 answers. And that's the wrench that's in the works here, so to speak. So case 1, there can be this kind of thing. Suppose B is the base and A is over here. And I'm given side, side, and angle like that. This is angle alpha since it goes opposite A. And I don't know how long this side is. I'm just given these side lengths and I don't know what this angle is. And this angle. And so this goes out here somewhere like this. You know what? If B is greater than A and alpha is too small, too large, large enough depends on how big B is in relation to A. What can happen? Think about it. I love this picture that books always draw. You can swing this one any angle you want. So this endpoint here can go in a big circle like that. But you cannot intersect this ray out here if it's at a steep angle, right? So there's no solution. There can be 0 solutions given side angle data. So that's one possibility. If the base here is longer than this side and this thing is too large, and you just can't make them intersect. The second case is this. If you have an angle here and a side here, with this side bigger than this side, and alpha is just large enough. What can happen is you can just take the side, and if you swing it around just right, in this big circle around which you can swing, it just touches at this one point along this ray, right? This is alpha. You're given A, B, and alpha is the idea. I should put that up here. Given A, B, alpha, side followed by angle, side, side, angle. I drew it counterclockwise, but it can also go clockwise. It might be that this swinging this around in a circle just touches this ray in one point. So there's one solution. Or it can be this kind of case. If A is bigger than B, then you have this kind of a case. Now it doesn't matter what the angle over here is. There's only one place I can intersect it. This swings around in a circle like this, right? And it can only intersect this ray in the one spot. So if A is bigger than B, or B is bigger than A and alpha is just large enough, then there can be one solution. Not critical that you memorize the geometry. I just think you'd like to see that so you understand it. Sometimes that gives you a hint before you start solving it, what you expect. Right? Having intuition is always helpful. Right. But the point is there can be no solution. There could be exactly one solution in these cases. Or in the third case, you can have a triangle like this. B is bigger than A. And alpha more than just large enough to make a right triangle. Alpha is not too large. Then I get this kind of a case. I can make a triangle like that just touches at this angle alpha. So again, I'm given A, B, and alpha. And this ray comes out here And I can intersect it right there, right? But that's not the only thing, right? Oops, I should make this a little more obvious. I can intersect it right there and make a triangle. However, there's another case, right? I can swing this to any direction I want. I can swing it around in a big circle. The circle comes around and also touches over here somewhere. And I can make a triangle like this. So the blue triangle is one solution that has A for this side, B for this side, and angle alpha over here. And the white triangle is another. There's exactly two solutions. Well, that's a real nice way to visualize this that you'll find in your textbook. But the side-side angle case is not a congruence theorem. It can have no solution, exactly one solution, or exactly two solutions. But fortunately, that's it. It's not more complicated than that. This is those nasty details I was referring to. All right. So we need an example. I like this example because it illustrates how intuition can play into this. All right. Suppose A equals 2, B equals 7, and alpha equals 80 degrees. What do I know immediately just by thinking with some intuition? Anybody see it? I think it helps to sketch these. You don't have to, it's not required. You can do all this without sketching if you want to do numbers. But a sketch makes it obvious. B equals 7, like that, right? A equals 2, it's a little shorty. There we go. It can swing around like that, but alpha is 80 degrees, nearly a right angle. I can never make this little 2-inch side swing around and intersect this 80-degree angle over here, right? Evidently, we'll say no solution. If you don't figure that out by looking at it, then you can do the following procedure and prove it, right? However, we can check. Make it rigorous, right? According to the law of sines, I want to take, and by the way, I don't have two angles, so I can't do the sum of angles theorem first, right? Sine of alpha is to A. Here's an angle on opposite side. I'll say sine of 80 degrees is to A 2, as I have to use the B in here. Sine of beta, the angle opposite B, is to B equals 7. So there's the, by the law of sine star, the equation of the three that uses all three of these numbers and leaves one unknown, right? There's the law of sines to try and solve this problem. Now I just multiply both sides by 7. And I've got 7 sine 80 degrees over 2 equals sine beta. And now if I just run this on the calculator, I wonder what it is. Seven times sine 80 closed divided by 2 gives me 3.44. We'll round it to 3.4. How do I know that has no solution? This is an important point. It'll save you a lot of work sometimes. Sine of an angle is always a number between plus and minus 1. Remember, it's a graph that looks like this. Here's beta, here's y. This is a graph of y equals sine beta. And it goes up as high as 1 and down to minus 1. I'm asking, for what angle is the sine equal to 3.4? The sine is never equal to 3.4, right? It's never got this y coordinate. It stays down here. So you can never solve this equation. It has no solution. In fact, what you might try at this point, if you're still not convinced, is try taking beta equals the arc sign to see what angle has that sign, and it will say domain error. And that's the indication that there is no such angle. It means, right, the arc sign can't be evaluated. If arc 3.4 doesn't exist because there is no angle whose sign is 3.4. All right, so there it is, the no solution case. What will happen is you get sine beta equals a number bigger than 1 and say, no solution. Easy, right? Just have to do all these different cases. Let's try this example. Well, I have A equals 4, B equals 3, and alpha equals 110 degrees. Not a special angle, right? How do I solve this one? Here's what somebody's going to do on the test. It always happens. I know C is the square root of A squared plus B squared is 5. I've got the other side, right? What's wrong with that?
That's for a right angle.
Yeah, it only works for right triangle. Don't use the Pythagorean theorem on an oblique triangle. Pythagorean theorem doesn't work in this section. Thank you. Pythagorean theorem is only for right triangles. Don't use it here. Use the law of sines and the sum of angle theorem. So it's not a 3, 4, 5 triangle. I wonder what it is. Two sides are 3 and 4, but the third side is going to be something else. I know I'll use the law of sines because after all, I'm given B equals 3. Make it shorter here. A equals 4, a little longer. And alpha, this angle opposite A, is 110 degrees, about like that. That's the triangle given. Look at what intuition that gives you. Now you can see, right? But there's only going to be one triangle. This is the one triangle case. Formally, you say since A is bigger than B, you're given A, B, and alpha. There's just one solution according to what we said over there. But right, again, if you swing the circle all the way around, let A swing around to an arbitrary angle here, you can only intersect this ray in one point. So this is going to be our triangle. There's going to be one solution. We can already see it by drawing it. But if we didn't know that, it doesn't matter. Watch what happens if you don't draw it. You can still figure it out. What do? We use the three things we're known to find one more. Since we don't have two angles, we're going to have to use the law of sines first. By the law of sines, our star equation right here. Here's the good thing. We only have one equation today. Doesn't that sound easy? Unfortunately, lots of cases, right? So by star, what we write is an equation that relates these things. I need sine of alpha is to A. Sine 110 degrees is to A4 as sine of beta is to B3, relates these three numbers, at least one thing unknown, beta. How do I find beta? I can multiply through by 3 and say this is equivalently 3 times sine 110 degrees over 4 is equal to sine beta. And now, what could beta be? This is where the ambiguity really sets in. One idea is obviously I know one angle whose sine is equal to this number. If I compute this, it's less than 1, so there is a solution. Given that this is less than 1, between -1 and 1, you can always find an angle with that sign. One solution is always that beta is the arc sine, right? 3 times sine 110 degrees over 4. What is that? Let's run it in the calculator. This section is one of the main reasons I told you have to have a calculator for this class. Arc sine of 3 times, oops, it did sine. No, I didn't. Sine 110 close divided by 4 close, and I get 44.8 if I round to one decimal place, 44.8 degrees. I mean, I like to write squiggly equals. You don't have to do that. It's approximately equal to that. That's how I rounded it. All right, so case 1, I can find beta by using the arc sine. Now I have 2 angles, so I can immediately find gamma. So here's let's see, step 1. Step 2 is I find gamma is 180 minus the one I just found, 44.8, minus the one I'm given, alpha was 110. And let's see, this is 144.8 is 35.2 degrees. No, 25.2. Yeah. So law of sines to find the first angle. Now I have 2 angles, I'll find the last angle, and then finally I'll use the law of sines to find the last side. I can't use the Pythagorean theorem. Right? So we'll say, and by the way, next time you'll see a nice reason you can't use the law of the Pythagorean theorem. For oblique triangles, the law of cosines is a generalization of the Pythagorean theorem. It will show you clearly if an oblique triangle, c squared isn't a squared plus b squared, it's a little more, right? So we'll use the law of sines here and we'll say, well, sine alpha 110 degrees is to A for, as I'm trying to find C, so I'll put sine gamma, the one I just found, is the C, and I can solve for C from that. At this point, I'd like to make a comment. We saw the law of sines, written sine alpha is to A, as sine alpha beta is to B, as sine gamma is to C. A lot of textbooks prefer to write it this way. This is just as true, and you're welcome to write the law of sines this way anytime you want. You can also put it upside down. A is to sine alpha, as B is to sine beta, as C is to sine gamma. This is just as true as the way we wrote the law of sines. This is also called the law of sines. It's just the same rule written upside down. This one is sometimes preferred because it's faster. If you want to write it this way, go ahead. Lots of textbooks do that. That would have been easier here. It would have saved me a step. I got to solve for C. What do I do with the next step? I'll turn these upside down now. So it's an extra step. If I would have written it this way at the first step, I would have saved one, right? So write it this way if you want. I'll just say this is an alternative law of sines, the star. Alternatively, star is this. I could have started at this step and just written 4 over sine 110 equals sine 25.2 degrees. Oops. C over sine 25.2 degrees. And I could have saved this step if I would have written the law of sines this way. So you can do that whenever you want. Now, move this over a bit. I multiply both sides by sine 25.2 and I get sine 25.2 degrees times 4 over sine 110 degrees is equal to C, and I just have to do the calculator. Let's see. .812. So I get C is approximately 1.8 to one decimal place. There we go. I was given 3 pieces of information and I found 3. Oh, wait a minute. There could be 2 solutions, right? This is side-side angle, in case it brings ambiguity, right? Maybe there's a second case. What is the second case? Here's what always happens in the second case. What you always wind up with in the law of sines is the sine of an angle equals a number. So sine theta equals some number. In this case, it's 3 times sine 110 degrees. Well, let's just talk, suppose it's some number y0. Suppose that's what our sine of our angle is in case 1. What we said was that one solution is the arcsine. And how we get that is we say the sine of 8 is equal to this y coordinate. We draw all points with y equals that y coordinate. And we realize that there's actually 2 angles it could be, right? So in step 1, we try to find all angles whose sine beta is y0. One of them is the arcsine. Which one of these 2 terminal rays corresponds to the arcsine? Remember, the arcsine is always a number between plus and minus 90 degrees. So this one must be the arcsine. Whatever number you get in step 1, y0, the arcsine will be one solution. But now this terminal ray corresponds to a second solution. We can't count these. We can't count going around like that because there's only 180 degrees in a triangle. We can't take any angle that's bigger than 180 degrees when we won't have a triangle, right? So it's only these 2 angles here. We can't go backwards. That'll be a negative angle, right? Triangle angles we always call positive. So it's this one and this one are the 2 angles we're looking for. It's this one. It's easy. If this one is arcsine y0, then this one by symmetry is also the arcsine of y0 if we run it counterclockwise. Right? Just by symmetry, it goes up the same height, so it's the same triangle here and here. That being the case, this angle right here is 180 back up the arcsine. So whenever you apply the law of sines to a case that has a solution, there's 2 cases, the arcsine and 180 minus the arcsine. So now I'm going to say case 2, instead of saying beta is the arcsine of 3 times sine 110 over 4, the other case is that beta equals 180 minus that number. There it is. And since we already calculated this angle, we don't need to recalculate it, right? This was 25.2. So let's see, we got 154.8. There it is. Now what do we know? This is impossible. So how do we know it's impossible? We already have an angle, it's 110 degrees. If we add to 154, we got more than 180 degrees total, right? So what's better, if I can back this up for a minute, is to notice back here, since I'm given A, B, and alpha, if A is bigger than B, there's only going to be one solution. I can see it from geometry, and just do the one case of arcsine. Then I wouldn't have to spend my time on that, all right? But if I don't recognize it or I don't draw the picture, I'm not sure. It's really easy to be not sure. Then I write out case 2. Beta is 180 minus the arcsine. If I add all the angles too big, then I add up to more than 1. So if you don't draw the picture, you'll still find out as you go along. You'll get an impossible triangle with angles bigger than 180. Any questions on that? This is the toughest part of the lecture today, probably the toughest part of the rest of the course. All right, so this is the case with one solution. It's this triangle we already figured. C equals 1.8. Gamma equals 25.2. And beta equals 44.8. We've got that one triangle solved. All right. Moving on to the worst. Get it over, huh? But you see, that wasn't a 3, 4, 5 right triangle, right? Because it wasn't a right triangle. I suppose I did this one. Suppose this time A equals 3 and B equals 4. And alpha is equal to, let's say, 45 degrees. Right? How about that? How many solutions do you think there are now? Again, intuition can give you some guidance. Sometimes you look at it and say, oh, no solution, right? That first one, it's easiest to look at it and say, oh, there's only 2, it can't possibly reach over here. Right? Let's see if that happens here. B is 4, A is 3, a little shorter, 3/4 that length. And then alpha is 45 degrees. That looks like maybe I can do it. Sometimes it's hard to be sure. You can't always tell, right? Something like that. Moreover, if I think about it, not only can I close the triangle that way, I can make a side length 3 here and close it this way. This looks like the 2 triangle case, intuition says. Let's see if it is, right? Again, you don't have to draw the picture, but it sure helps, doesn't it? What do we do in the side angle case, right? Again, you can see this is side followed by angle. So it's the ambiguous case here. We'll take the side the opposite angle we know, sine 45 is to 3 as, and we want to put this one on the other side. B is 4, so it must be sine beta is to 4. Now we know 3 and the 4 quantities, we can solve for beta. Just like in the last problem, we'll multiply both sides by 4 and get 4 times sine 45 degrees this time over 3 equals sine beta. And we progressed it before, we say, oh, there's 2 cases, right? Beta is the arc sine or beta is 180 minus the arc sine. Those are always the 2 cases, right? And if one of them doesn't work, we'll find out because we'll get impossible angles adding up to more than 180 degrees. I'm recording this video. This might not be a bad one to go back and look at because there's so many details here, right? So case 1 is that beta is the arc sine. That's always a solution when you get a number between 1 here and you do indeed. All right. The other case, case 2, I'll do it over here. So it looks like we're going to get 2 cases this time. It's on the board still, barely, I guess. Is beta is 180 minus the arc sine. Of the same. There we go. And we just have to make 2 different triangles. So let's see, what's the arc sine? We'll run it in the calculator. And if we get a domain error, we know there's no solution, right? Arc sine, and if we get, and then we have to compute this angle and see if it's too big to see if there's 1 solution or 2 solutions. Arc sine 4 times sine 45 closed divided by 3 closed here When you get 70.52, we'll round it to 70.5 degrees. We can compute this one, theta must be 180 minus that. So it's 109.5. So it looks like it's okay, right? Because now I go on that step one is you find one angle. Then step two, you have two angles, so you immediately use the sum of angles theorem and say here that gamma is 180 minus this angle, minus the angle we were given. And let's say that's 110, 115.5. Leaves me 64.5, right? So by the sum of angles theorem, I get that here. And over here, if there's not a second case, then we'll get a negative angle. These angles that we have will add up to more than 180. Here, gamma, if I take 180 minus the given angles, 109.5 and 45, I actually get a positive angle, so there is a second case. If this comes out to be a positive angle, there's a second case. So let's see, 154.5 leaves me 25.5. All right, so I'm going to get two different triangles. Fine, I use the law of sines again. So two law of sines and a sum of angles theorem. Let's say I need to find C still. So I'll say sine alpha, 45 degrees is to A. That's within the original problem. I'll use my least rounded numbers. Right? Sine alpha is to A, and that's sine gamma, 64.5 degrees is to C. We'll find C. A little algebra. Let me point out something too. I've been taking reciprocals and then multiplying by the sign. You know what else you can do? You can solve this by algebra any way you like. A lot of people like to cross multiply. So I'll do cross multiplying here. You do it whichever way you like from algebra that you're used to, so you make less mistakes, right? Let's multiply. This times this equals this times this. That works too. So cross multiply says C times sine 45 equals 3 times sine 64.5. That's going to work also. Now I divide by sine 45. And I've got C equals 3 times sine 64.5 divided by sine 45. And see, that works just as well as taking reciprocals and then multiplying, like we did in the other ones. Maybe you prefer this method. Wanted to do this somewhere along the way. So 3 times sine 64.5 close divided by sine 45 close gives me 3.8 to the one decimal place. There's C, and I'm all done, right? The first case is that I have a triangle with these three angles. These angles, 70.5 and 64.5, and this remaining side, 3.8. The other possibility is I get these two angles, and then I've got to find the last side, C, and I'll do the same thing. Sine alpha is to A that we were given as sine of gamma that we found here is 25.5 degrees is to C. This time, again, if you cross multiply again, we'll get equivalently C sine 45 degrees equals 3 times sine 25.5 degrees divided by sine 45. And by the way, since this is an exact special angle, you are welcome to put in square root 2 over 2 here and multiply it in. There's nothing wrong with that. It's just, since you have to round these in the calculator anyway, there's no point in putting in the square root 2. It's going to not stay exact when you multiply by this decimal anyway. So you don't need to do any special angle tricks in here. It won't help you at the end because you have to multiply by something that's not special. All right, so this is 3 sine 25.5 degrees divided by sine 45, evidently, after cross multiplying and then dividing, gives us 3 times sine divided by sine 45 is 1.8. There it is. The most typical case, two different triangles are solutions. Side-side angle is not a congruence, and there's two solutions, two triangles that have those measures. There's the worst case right there. And now, a very important comment that you don't find emphasized in books typically. Check your answers. After all that work, it is so easy to make a mistake. Maybe we'll find one in here. Let's see. Kind of out of room, but I'll do my best to fit this in. I like to do what you call a sanity check. Right? Whenever you do lots and lots of calculations, assume there's an error in there. There's likely to be an error in there. Go through and just check things easily. You know, if you don't want to redo every step, it's too tedious. You won't finish your exam on time. But you can do the following easy checks. One, I like to do this. Check that the angles add up to 180 degrees. It's so easy to have a mistake in there. Get the wrong angle and it'll add up to 180 degrees. That's such an easy thing to do to add numbers to check, right? The second thing you can do that's real easy is you can make sure that this holds in any triangle. The largest angle is always opposite the largest side. If you didn't get that in your triangle, you made a mistake. Either one of them, right? I call this the three bears test, right? Big bear has the big meal or the big bed. Furthermore, the medium bear gets the medium bed, right? The medium angle is opposite the medium side. And the smallest angle is opposite the smallest side. So you just check two of these and the third one follows. But do the three bears test. Because it's such an easy thing to do, just look at them and see if which numbers are bigger, right? You don't even have to add them. Then make sure that the largest side length is less than the sum of the other two sides. So easy to make a mistake. If you do, it's usually a blunder. It's usually some big boo-boo, and one of these tests will fail. Here's what happens, right? If this side here, A is the largest, right? A, B, or C can be the largest. We're not requiring notation where C is largest. And suppose some of the other two angles, here's B and C are less than A, then guess what? That can be a triangle, right? A straight line is the shortest distance between 2 points, but this says B and C is less. So it's supposed to be able to go down. I can go down B and C and get across here faster than A. No, but it's an impossible triangle if A comes out to be bigger than, if the longer side comes out to be bigger than the sum of the other two sides. So those are easy checks you can do on this thing. And sometimes just when you try and draw them, you can see it. But let's try and draw these here. That's another possibility. You can kind of check these as you draw. I've got sides, let's say, of 3.8, 4, and 3. So 4, just about 4, 3.8. And 3. Maybe it looks about like that. 3 was A, so alpha goes opposite it. It was, I'm looking at the first triangle here. Actually, it was given. Alpha was 45 degrees. That looks about right. Beta in the first triangle was 70.5. That goes opposite B, that was 4. And then opposite 3.8, which was C, is gamma, is 64.5. All right, so there's the first triangle. Is that reasonable? We tried the three checks. Add these up. 70.5 plus 64.5 is 135, plus 45 is 180. All right, sum of angles checked. Is the largest angle opposite the largest side? Well, 70.5 is opposite 4, the largest one. Second largest angle, 64.5 opposite second longest side, 3.8 and 45 opposite 3. That's a check. And then finally, is 4 bigger than 3 plus 3.8? Sure it is. This is probably right. I didn't at least blunder, right? It's a subtle mistake if there's a mistake somewhere, maybe I rounded wrong in the last digit or something. I just copied the last digit. But it looks pretty good there. So case 1 is probably right. And now I try to draw case 2. And I say in case 2, once again, B is 4 and A is 3, but this time C is 1.8. So I've got 3, 4, and 1.8. So I'll draw it about like that. I hope you can see that on mine. I'm gonna have to draw these angles outside because maybe I better draw this bigger. 4, 3, and 1.8. Now I can draw it in here. Angle alpha was 45 degrees. That goes opposite the 3. Guess that could be opposite 4, which is B, is beta in the second case, is 109.5. There it is. That looks obtuse. That's probably right. And opposite the 1.8 was gamma, which in triangle 2 was 25.5. Do this if you have time at the end of the test. Check these things. Do these add up to 180? Let's see, 25.5 and 45 is 65.5. Added to this, I'm sorry, 70.5. Added to this is 180. Sure enough, the angle's out to 180. Right? Largest angle, 109.5 is opposite 4. Second largest, 45 is opposite 3. And then the third one follows. Third largest is opposite 1.8. That checks. The largest side, 4, is less than the sum of the other two sides, 4.8. So that checks. That's probably right too. That's not in the textbook because you don't need to do it. If you write, you're right. And this is just for you to make sure you can fix any mistakes you made. All right? Any questions on all that? All right. Well, now we're going to make another comment there. Let me move the camera here. When an obtuse angle is given. What's an obtuse angle? An angle bigger than 90 degrees in the triangle. So 90 less than the angle is less than 180 in the triangle. Suppose that's given. You don't have this case of having two cases. There can only be one obtuse angle in a triangle, and then what happens is the only solution for that ambiguous case is arc sine of the angle, not 180 minus the arc sine, because 180 minus the arc sine will be obtuse. You can't have two obtuse angles in a triangle. So when an obtuse angle is given, there is only one triangle. The 180 minus doesn't work. You don't have to remember all these rules. This is sort of intuition. What you do is practice these and see these things as you go along. For example, suppose I'm given A equals 12, B equals beta equals 40 degrees, and alpha equals 100 degrees. What case is this? Sketch it. I recommend. You don't have to. Let's say here's A is 12. And then alpha has to go opposite A, so it's way up there. I want to draw it bigger than a right angle. So maybe here's 100 degrees. And then let's put beta over here is 40 degrees. Opposite beta goes B. Opposite A goes alpha as we wrote it. And then this must be gamma over here. And this would be C over here. So I need to find B, C, and gamma out of this triangle. And I comply with the law of signs, right, because I'm given, let's see, angle, angle, side, in that order, rotating clockwise this time. I think I'm about out of time. I'll pick this up next time, yeah. All right. But you write the law of signs and there's only one case. So, to be continued. All right, let me give you the list of homework here. You might get started on it in the law of signs. We haven't quite finished. We're gonna do a couple more examples next time. But, look at 8.1, 1 through 11. Omit 12, it's on finding an area of a triangle that we definitely haven't covered yet. If you have trouble with these, bring them to class next time and we'll work on them, but we're gonna do at least one more example anyway. Have a nice rest of your day. Thank you for coming in.